people that have signed in. Okay, it's time, so we'll start. So thanks for coming. I hope this is informative. Some of you have certification exams, and others maybe you just want to refresh some skills. So plan is it's a two-part section today. The first section is going to be about basic lab math, and because I suspect that no one would come to a 3-hour session, we'll just do it in an hour. And so I'll only go over basic concepts and just a few sheets. And then the second hour will be about interview skills and writing a CV. And pragmatically, I focused it on how to get your first lab job, but that doesn't necessarily mean that we can't go over things like how to interview for a professional school or a graduate school. So depending on how much time we have and what interest there is, we can do that as well. So, lab math review. I'm going to start with really basics, but also keep it really good. So, scientific notation first. You'll need to understand scientific notation, and everything I say can't be an exercise for you. It has to be second nature for you. And those are two vastly different things, right? And so I think this will become most apparent when we go to the metric system. But anyway, everything I say has to be second nature, not some sort of mathematical exercise. Because in the real world, it will never be the point of anything you do. Understanding these things will never be the point. These things are a tool set, and you'll use the tool set over and over again to do the actual thing you're supposed to do, to get to the point. And so we'll build up some competency today so that you understand, what do I need to be measuring to make a solution? And the calculations that we'll go over are not the point of what you're doing. The solution, making that thing, delivering that actual object, that chemical, that solution, that whatever, that's the actual point. So this stuff has to be quick, and it has to be second nature, and it has to be without limitation. Like any skilled artisan with their tool set. So, scientific notation. The issue we have in science is that we deal frequently with things that are very, very plentiful or very, very few, small. And so we deal with numbers that are huge or tiny, sometimes in the same operations. And that becomes really cumbersome and also, honestly, error-prone. And so we've tried to simplify things, reasoning that most of us can actually deal with moving decimals and with multiplying and dividing by what we call orders of magnitude. And orders of magnitude are just powers of 10. Right? And so scientific notation relies on that and tries to give us a simplified mechanism to actually express really, really large or really, really small values. And so if the number is too large or too small to be convenient, we'll use scientific notation, and that will use exponents, aka orders of magnitude, or in simple language, powers of 10. And so any number that is not equal, how do I do this? I'll do it, I'll start. That is not equal to 0. You can express as a times 10 to the power of b. A times 10 to the power of b. And so, let's actually pursue that. All right, so let's pick a number. I know, I've got one. Let's use the number 1. We have to start somewhere. 1. So that would be a times 10 to the power of b, and so that would be 1 times 10, 0. All right? Okay, well, let's use that concept that I talked about of orders of magnitude. And let's increase my initial number by an order of magnitude, which is a multiple of 10. And so let's do 10. Like that. All right. Let's increase the initial number by 2 orders of magnitude. Like that. And so on and so forth. And so if I were to increase the initial number, which is 1, by 3 orders of magnitude, I would end up with 1,000. And that can be expressed as 1 times 10 to the third. All right. Well, I could go on indefinitely, obviously, but what if I want to express numbers that are small, that are less than 1? Well, let's decrease my initial choice by an order of magnitude. And so let's consider 0.1. You would express that as 1 times 10 negative 1. Let's decrease my initial choice, which was 1, by 2 orders of magnitude. That would give us 0.01. You can express that as 1 times 10 to the negative 2. And 0.001 as 1 times 10 to the negative 3. And so on and so forth. That's the basics. And of course, you can also use numbers that have decimals. And so 110, for example. Anybody? Okay. The masks are yeah. Okay. 1.1 times. Yes. Okay. And so on, right? All right. So that's the basics of scientific notation. And the way that you actually deal with numbers that are expressed in this format is mathematical. That's simple math. And so we'll leave that out of the discussion today because I'm here more for the practical applications. And so this kind of thinking comes into play not only when you want to express a number that's very, very big or very, very small, but for example, and this will never happen to you, you'll never make a mistake, but other people may make a mistake. And they'll have to discuss with you how badly they've made that mistake, right? And frequently people will say in the lab, no, that calculation is off by 2 orders of magnitude. Now you understand what that actually means. It means that you're off by a factor of either 100-fold too concentrated, for example, or 100-fold too diluted. That's what 2 orders of magnitude means, right? So we think in these terms because frequently it's not just the actual value that we're dealing with that's very, very big or very, very small, but related values or derived values are also going to be very, very big or very, very small. And so we'll talk to one another like this. We don't just write these things down. People will say 10 to the 6th more and things like that. Right? Those are expressions that are actually used. So have a look at scientific notation if you're going to A, enter the workforce certainly, and B, take any of the certification exams. Right? Significant digits. This is a bigger subject than I have time to actually address in 1 hour for a variety of reasons that can be frustrating. One is that there's a distinction I think that you can and probably should make between how you calculate things and how you operate in the lab. And I'll tell you what I mean about that. So the gist of using significant digits is to make sure that when you actually manipulate data mathematically and derive values from data sets, you want to make sure that the mathematical expression of your results actually reflects the capabilities of your instruments. So if you take 2 measurements and then you have to actually manipulate the measurements mathematically, and the measurements were down to a milligram, because the best scale you have, the best scale you can muster, can measure reliably a milligram. But when you multiply or divide or add or subtract numbers, you may get these mathematical results that have an amazing amount of decimal places, right? And so, in theory, you are now calculating picogram quantities. But I said the word that's the problem, calculate. You can calculate things, but they don't necessarily reflect the actual resolution of the system you're using, right? And so the idea behind significant digits or significant figures is that your mathematical expressions, the results as you present them, should reflect the limits of resolution of your system. They should reflect the resolution of your scale, the resolution of your balance, the resolution of whatever instrument you're using. Your meters, instrument is going to have resolution limits. And the way that you express values should reflect those resolution limits, or at the very least, not be misguided. Because you can generate these mathematical answers that have a significant, or an amazing, I'll say that, an amazing amount of digits, but not all of them are significant. So, there are rules. So let's examine the rules, and let me move here. So I'll just summarize the basic rules that I think you should all know, and there's more to it, but if you know this and you understand this, you should be able to function more than adequately in language. First rule. So let's separate numbers into two general categories. Things that are 0 and things that are not. Okay? That's how we'll start. So, non-zero digits and this is important. If and only if they are within an instrument's capabilities. In other words, if they are actual measured data. Keep that distinction in mind, because you're not going to be doing just math problems, right, in a class. You'll be working in a lab. And so, for your workspace, non-zero digits that are within an instrument's resolution or capabilities are always significant. If you can measure it, it's real data, it's significant. So, let's look at a practical application. Let's say you're using a scale, right? And you get this value. And the scale measures in grams. Perhaps I'm jumping a little ahead, but I'm going to assume you have a working familiarity at least with the metric system. And so, if this instrument is accurate to 1 milligram, which is 1/1000th of a gram, as we'll review in a bit, that means that this value is real. You could measure 1 milligram on that instrument. That is within the resolution of the instrument, right? So that means that this value comprises entirely significant digits. All of the digits are significant. 1, 2, 3, 4, 5, 6 significant digits. But let's say that your scale isn't as fancy and doesn't accurately measure down to 1 milligram. Let's say that your scale will only measure to 0.1 grams. Well, now it's a different story, because what that's really saying is that, you know what, I can measure to this value here. So this is real. But those two digits are not within the resolution of my instrument. So this same number would now have 4 significant digits. This is a 1 milligram resolution. This is a 0.1 gram resolution. You see the logic? So keep that in mind. Now, as I've written it, and as I've explained it, it's confusing. It's confusing, right? Because someone that walks in the room won't know what I'm actually talking about. It won't make a lot of sense. And that's almost universally true. So you can't leave matters like this if your scale has a 0.1 gram resolution. You can't leave matters like that. That's the point of significant digits. And so, if this is the case, you have to represent the number in a way that actually reflects the resolution of the instrument. So what do? Well, this measured value becomes you see what just happened? You recognize the resolution of your instrument, and you acted accordingly by actually adjusting the way that you represent your data to reflect the resolution of the instrument. So you really did is you rounded this, didn't you? And you made a decision based on how many significant digits you can actually represent. Here, your limit was 4, and so this number has 4 significant digits. Okay. Now, conveniently, I dealt with numbers that are not 0. What about zeros? And so if you think about it, for any number, for any value that includes a 0 as one of the digits, there's 3 choices. The 0 can be internal to the number. It can be external in 2 different ways. Either a leading 0 or a trailing 0, as we say, right? So let's look at those individually. So let me go here. Second rule. All zeros between non-zero numbers are significant. Again, considering and within the limits of resolution of your system. Within the limits of resolution of your system, all zeros between non-zeros are significant. So, here's an example. 101. That 0 is between 2 non-zero numbers. If and only if you can actually accurately measure with whatever it is you're measuring, 101 units of whatever it is we're dealing with, then that 0 is significant, and so this has 3 significant digits. Well, let's deal with the decimal, and let's keep it simple. Two internal zeros, again, within the resolution of your system. This has 6 significant digits. Okay? All right. Next, let's deal with zeros to the left of non-zero numbers. So leading zeros. So let's give you an example. And let's think it through in terms of a scale, which is an instrument that everyone uses. And so here's our example, 0.039 grams. Our scale can measure milligram quantities. 0.039 grams. So that value is what you actually may see on the display. And it's got 2 zeros in it. But of the 4 digits total, you have to now actually determine how many are actually significant. And there's a way that you can reason this to figure out how many are significant. So that number has zeros in it. And it's a value in grams. Is there a way where you could express that same quantity? It's a weight, right? Can you express it without the zeros? If you can express it without the zeros, as you're pointing out, then those zeros must not be significant, are they? So, isn't this 39 milligrams? Right? So now what have you got? In a sense, you've got the same thing you had before, which is a value that has two significant digits. See the logic? Okay. Now, what about zeros to the right? So, zeros to the right of a number, let me give you an example. Something like how many significant digits are in this measured value? And it's a loaded question because everything that I could possibly do or say to confuse the issue has been thrown in. I've got trailing zeros, and I also use the term measured value. Remember, we're always considering and only considering significant digits with respect contextually to what we're actually doing and what we can actually measure, the limits of resolution of our instrument. I said that's a measured value. So what does that really mean? For example, does it mean that it could have been any other combination of digits for the last two positions, and they would be real because I could measure them? And it just happened to actually be 1.2300 grams. In other words, does my scale have resolution down to what? Nanograms, yeah. 200s of nanograms? Or not? So let's deal with the possibilities. So we're on 4, rule 4. Zeros to the right. They are significant only if they are within the limits of resolution of the instrument. Emphasis mine. What that really means is that if you can measure accurately 200s of nanograms on that scale, then that initial value, 1.2300 grams, is an actual measured value. That means that all these digits are genuinely significant, they're actually significant. What if you're using a scale that can only measure to 1 milligram? So let's think about this. If your resolution is hundreds of nanograms, this is the position we're talking about, and that is real. So this has 1, 2, 3, 4, 5 significant digits. Same number. If your resolution is 1 milligram, how many significant digits? Or what if your resolution is, and let's combine this principle with the previous rules. only down to 0.1 grams. That means only this position matters. The rest is artifactual, literally. And so then you would have two significant groups. And the way you represent the number to another person would have to change accordingly. And so in this case, you use all the digits because they're all actual measurements. In this case, well, this becomes in this case, you've got to do a little rounding. Make sense? But you're stretching, and so am I, because it is confusing. And so, if only there were a way to represent what we can actually measure to the next person that actually deals with the data set. In fact, there are several ways. So there are ways to actually tell you, for me to actually convey to you, whether we've met or not, if you're reading something, that, you know what, I measured this. This is not artifactual. Anything you do in the future, any manipulation you do in the future with that data set, has to include conceptually that I can measure down to hundreds of nanograms. I measured that. I can do that in various ways. The easiest way for a number that already has a decimal is to use an overline. So, how do I tell you, you know what, we're real here? This is measured. Now there's another way too, but that can get a bit confusing. Typeset or writing and so on. And that is using a dot or a period. And so for whole numbers, I would actually consider using a period. You can always use an overline, but if you are actually trying to represent 100 grams, the implication being it's not 99 and it's not 101. It's 100 because my resolution is a single unit. That does it. So trailing zeros emphasize this practical concept of our dependence on resolution, on the resolution of the instrument. Okay. Now, eventually, you'll have data sets, and you'll know how many significant digits each value actually contains. But now you have to actually do operations with the data sets. You have to manipulate the data sets. And so what kind of manipulation are we talking about? Well, simple math. Multiplication or division, which is essentially the same thing, or addition and subtraction, which is also essentially the same. So let's look at the rules for actually multiplying or dividing first, and then we'll look at adding and subtracting. If the operation is multiplication or division, it doesn't really matter how many numbers you're multiplying or dividing, and it doesn't really matter how many significant digits each of those numbers has, as long as you recognize the following. When you are multiplying or dividing, the number of significant digits that should be represented in your answer depends upon that number that you operated on with the least number of significant digits. And I could probably try and make a statement that's more confusing, but it would take a little bit of time. That was pretty confusing. Let me just give you a general example. You've got a bunch of numbers to multiply, okay? One has 5 significant digits times 3 significant digit numbers, times a number with 2 significant digits, times a number with 8 significant digits. Based on what I said, the way I said it, your answer is limited to 2 significant digits. Your answer is limited by the number of significant digits that is the smallest among the initial values. Now, does it make sense? Okay. So this would give you an answer with 2 significant digits. Now, what if you're adding or subtracting? That's an A, believe it or not. That's an A. Let's say you are adding a number that has 3 significant digits, 2 decimal points. Plus 5 significant digits. And 1 decimal point. When you are adding or subtracting, what you need to do is consider the value that you've measured accurately with the least number of decimal points. And that's why I specified it. So let's give you a real life example. So 3 significant digits with 2 decimal points. 3.14 grams, let's say. Or let's make it something else. Let's make it 7. Plus 5 significant digits with 1 decimal point. Okay. 1, 2, 3, 4.5 centimeters. Okay. Which of these 2 numbers has the lowest number of decimal points? This one's got 1, this one's got 2. Our answer is limited to 1 decimal point. And I should be saying decimal places. See the logic? So let's do that. Someday I'll tell you the story of losing my calculator. So the actual mathematical value that I get is 1,237.64 centimeters. But I have to consider the rule here. And so this becomes 1,237.6. Okay, so the rules differ a bit depending on whether you're multiplying, dividing, or adding and subtracting. Yeah?
If it was 0.68, would we round it or keep it at 6?
I did round it.
Like round up?
Yeah, if it was above 5, you would round up.
Okay.
Yeah. That's what I'm doing, I'm rounding. Okay. Questions so far? I'm going fast because we're on the clock, literally, and I want to do lab math too. All right, next, the metric system. So, I want to preface this again. The metric system is not something that we do as exercises, and it's also not something that we do in the lab in terms of converting units that are non-metric to metric. Almost invariably, and for me it's been virtually career long, I've dealt exclusively with metric units, or really the metric system. It's got a long history, and sometimes actually political too. And it used to be related, for example, the meter, to the distance physically between the North Pole and Paris. Anyway, it's now they use atomic values and so on, but ultimately it's a subset of the international set of units that scientists use. And so that's called the International System of Units, or SI. So the metric system that we use in the biotech laboratory, unless you're doing things that are purely chemical or purely physical, is a subset of SI units, and we do a few things uniquely as biotechnologists, and I'll go over those exceptions. In other words, we use some units a bit improbable, really, but we get away with it so far so good, and I'll point out those exceptions too. So, subset of SI units that we use on a daily basis has to be just that. It has to be something that you can use on a daily basis. And frequently, not all of my students, but those of you that have been my students may confess to you that they were very confident they understood the metric system until I asked them how much I weigh. Or I asked them the temperature in this room. Or I asked them how tall I am. Or I asked them the distance to their house. Or how many liters of fuel their car takes. These are everyday values. If you don't know them, you probably don't know the metric system as well as you might think. And I would recommend you become very fluent in the metric system, because that's how we talk in laboratories. And I think I'm walking proof of that because I genuinely don't understand things like Fahrenheit and miles. And I'm not making this up. I don't get them. Because I don't use them. I don't use them in my everyday life. I use metric units in my everyday life. And so when you pick something up, this is about a kilogram, probably less. It's maybe 700 grams, right? Go to the grocery store, pick up a 2-liter bottle of soda. That's what 2 kilograms actually feel like in your hand. This will make a difference in your career. Not because you'll know how much soda weighs, but because by understanding how much soda weighs, and by actually living in the system, you'll be able to avoid gross mistakes. You won't be able to avoid things like, no, I should have measured 10.45 grams and I got 10.46. No. But if you're off by an order of magnitude for virtually anything, you should be able to catch yourself if you really understand the system. And if you really understand the system, you can talk in shorthand very, very quickly with other people within the system. And it takes only seconds, and it takes 0 calculations and 0 thought. It takes no thought for me to tell you I'm a meter 83 tall or 183 centimeters. It's the same number to me because I understand the system. So get that fluent. And the question is, how do you do that? Well, one way is you struggle through it in labs over and over again, and you're going to make mistakes. And there could be shortcuts. One shortcut that I do recommend is flip your phones over. Flip your phones over. Make everything metrical. Start thinking along those terms. When you go to the store, pick something up, look at the weight in grams, and you know what, this is what, so a tin of soda, for example, that's typically 333-ish mils. That's 333 grams of essentially water in aluminum, which weighs next to nothing. That's what that feels like. I actually get that. And so I can eyeball something and tell you that this is, if I'm measuring 50 mils and this is what I come up with, that's drastically wrong. It's wrong by an order of magnitude. I can do those things. So practice, I think, makes perfect. And it's a great system to learn because, well, it's easy. And that's why I like it. I don't like it because it's complex. I like it because it's simple. So, let's go over the units and the multiples of those units. So, what we do in the laboratory differs a bit, as I said, to SI units, and so we do things only a little unconventionally for specific reasons. So, distance. The meter, and the symbol is little m. Mass. The ground. Symbol G. Volume. The liter. Here, really the symbol is a little L, but it becomes difficult to actually represent, especially in typeset. And so some textbooks will actually, instead of writing a little L like that, because that looks like a 1 or who knows what else, they may use a big L. Or, I get away with it because I'm sloppy. And you can tell that that's not a 1, even by my standards. Quantity. Someday, maybe it's already happened to you, it'll happen to all of us eventually. Some chemist is going to tell us about Avogadro's number, and the number of atoms in 12 grams of carbon-12. In any case, there's a particular unit that we use for quantity. That's related to all those things, and that's called the mole. The symbol is mole. Okay, so far, so good. Anyone from other disciplines will recognize that we're using all those units correctly. Here's where we take a few steps to the side, and we have reasons to do so. Weight. Not mass, which is a property of matter. Weight. What is weight? Weight is an expression of force, isn't it? How do we do that? Well, I'll show you how they do that. Okay, so weight. And I'll clarify, we're really talking about force. Correct way to express weight in the laboratory is, yeah, you all said it universally, the Newton. You'll have noted, of course, that none of our scales actually measure it. And it's actually okay, because we're doing everything on Earth. And so we can take a step to the side, and we'll still use newtons in some ways. And so, for example, if we're talking about torque, we'll use Newton meters and things like that. But for everyday measurements in the laboratory, where I tell you, make me 500 millimolar salt, you'll grab sodium chloride and you'll weigh it out in grams. Grams. Grams instead. And we also take another side step when it comes to temperature. The reason we do that is because, well, in biotechnology, the whole point is to make things and solve problems and devise solutions using entire organisms or parts of an organism down to a molecule, right? Well, organisms are essentially aqueous, and we're dependent upon the physical properties of water. And so whereas temperature ought to be expressed in Kelvin, those values don't actually reflect the physical properties of water. Luckily, there's a similar scale that does reflect the physical properties of water. This is devised by someone named Celsius. And so what he did is he considered for his scale of temperature the freezing point and the boiling point of water. As it so happens, both he and Kelvin used the same magnitude for each degree. And so if you think about the amount of available energy or the difference in energy between any two consecutive values of temperature in Celsius or Kelvin, that energy difference is the same. The degrees are the same size, so to speak, in other words, right? But they're a different scale. And so, whereas the Kelvin deals with absolute zero, where matter is really, really interesting, but not for us in the biotechnology laboratory. Celsius deals with the freezing point and the boiling point. And so we use Celsius instead. Another deviation that we take is when we express time frequently. Unless you're doing something specialized and really interesting. So let's say, for example, you're a neurobiologist and you are looking at synaptic signaling or something like that. You are generally dealing in milliseconds and responses in an organism that take fractions of a second. But if you're growing cells overnight, right, that's a 12-hour period. So whereas time is properly measured in seconds, we do that, but for the sake of brevity and simplicity, because most of us deal with larger quantities of time than a second, we will also use hours and days and minutes and so on. Okay? So that's another thing to note. Okay, so all right, so far I've just told you a bunch of units. And you may argue, well, those units are merely different to non-metric units. They don't show any inherent advantage. That would be true if this were the gist of the argument. But what's really neat about the metric system is that you can express orders of magnitude or multiples of 10 consistently across the units using specific prefixes. And so you can use relatively simple language, especially if you speak Greek, which I recommend, to express orders of magnitude of any metric unit. And you can do the same linguistic constructs regardless of the unit itself. So there are prefixes that always mean the same thing mathematically, and we can use with any of the units. And so let's look at those prefixes and how they relate to magnitude. So I made us up a little plan because whenever I do this, I always run out of board space. So let's say that you have a metric unit. It does not matter which unit you're dealing with. Is it meter, the liter, doesn't matter. The unit. I'll put the unit here. It can be any of them. If you've got 10 of them, you would use a prefix to represent that you have 10 of those units. The prefix is delta. If you've got 100, the prefix is hecta. If you've got 1,000, the prefix is kilo. And see what's happening? For different orders of magnitude, we have different and specific prefixes that will always denote that order of magnitude, but it does not matter what unit we're talking about. We could be talking about liters, or meters, or grams, and so on. It does not matter. The same prefixes mean the same order of magnitude of that base unit. If you've got 10 to the 6th, the prefix is mega with a big M. 10 to the 9th, giga. And so on and so forth. And you can look it up, it goes, tera, and so on. Now, what if you have less than a whole? There are a different set of prefixes that you can use following the same principles. And so, let's say you've got 1/10 of that unit. Decimal. 1/100th of that unit. Let's say the unit is a meter. In most rooms, there's a meter stick on the doors. Let's say the unit is a meter. Well, that would be centi, the prefix. And that is where the now familiar centimeter comes from. It's 1/100th of a meter. Let's say you've got 1/1000th. Milli. And the numbers are going to get cumbersome, and so what I'm going to do is this. I'm going to give you the symbols instead. Let's say you've got 1/1,000,000th. That's the Greek letter mi. Micro. 1/1,000,000,000th. Now, and of course you can go to pico, femto, and so on. But notice what's happening. You can either express a lot or less than whatever base unit you want in orders of magnitude, which is always convenient because, again, we deal with numbers that are really, really big or really, really small in the lab, really convenient and logically. And by logically, I mean it becomes easy to convert, for example, from centimeters to meters, to kilometers, and so on and so on. Because you're just using decimal points and you're moving them around. So, let's say that the unit is a gram. That's my example. We've already used things like milligrams and nanograms in our previous discussion. And so now you see how it becomes convenient to understand what those prefixes actually mean. And you knew, because you've been through this, that milli means 1/1000, or 1 times 10 to the negative 3. And so there are 1,000 milligrams in a gram. But you also know there are 1,000 grams in a kilogram. And that brings me to another exception. How many grams are there in a megagram? I mean, that look is justified, actually. You may not have ever heard the word megagram in nature, because it may not occur in nature. What do we use instead, by exception, to represent 1,000,000 grams? Or 1,000 kilograms? A ton. Yeah. So a megagram really is a ton. That's another exception that I want to point out to you. Well, now I've pointed it out to you. So by rights, since I've more or less explained this, you should now magically be fluent in it, which really means you need to go practice this stuff. But here's the concept in general. What this allows you to do is say, all right, well, given that, and given that he's told us that a ton is 10 to the 6th grams. Isn't that also rather, and in fact I mentioned in passing, 10 to the 3rd kilograms? And let's think about it. Here's our unit. Yeah, a ton is 10 to the 6 grams. But the difference between a kilogram and a megagram, which is an odd way of expressing a ton, is 10 to the 3rd. 10 to the 6th and 10 to the 3rd differ by 10 to the 3rd. There are 1,000 kilograms in a ton. There are 1,000 kilograms in a ton. Or, as we said, 10 to the 6 grams, or 10 to the 9 milligrams. Because you look at the differences literally in magnitude. There are 1,000 milligrams in a gram, and for every gram, there are 1,000,000 grams in a ton. So the jump from milligram to gram is 10 to the 3rd. The jump from gram to megagram is 10 to the 6th. That means that the jump from milligram to megagram, which is a ton, is 10 to the 9th. And so on and so forth. So that's the gist of the metric system. Know the system. And so at some point, genuinely, know this is probably 15, 20 meters long, the room. It's about 22-ish degrees in here, maybe 23 or 4. It's a little warm for me. Outside today, it's going to hit around 30. That deli is 4 degrees. That freezer is minus 20. Know what these actually mean, and know what these things feel like. You'll walk into a 4-degree cold room. You may walk into a minus 20 cold room. They should feel different. And by understanding when they feel right, you'll also understand when they feel wrong. And by understanding when something looks right in terms of volume, you'll also understand when it looks wrong. This is, I guess, not dear, but it has a place in my heart because when I was a student, an undergraduate, I would have difficulty solving chemical equations and solving problems in chemistry because I didn't understand the magnitude of what I was actually talking about. And maybe this has happened to you too, where you're trying to calculate, for example, which brings me to my next subject, molarity or something like that, a measurement of concentration, right? And you come up with a number that is wrong, and if you understood the metric system, you'd know it's obviously wrong by, say, an order of magnitude or 2 orders of magnitude. If you understand the system and the system becomes second nature, then things should either look right or alarm you. And you'll catch mistakes that way. It makes a huge difference. And so you'll never again say, oh, the concentration of this solution I have calculated to 55 molar, which doesn't really happen. And you know it doesn't happen because now you understand the metric system. You know that it may be 55 millimolar or 5.5 molar, but it's not going to be 55 molar. Or the temperature is not going to be 275 degrees when you're dealing with a biological system. Something like that. Understand what the units actually represent and become fluent in the system, and I think you'll do really, really well in your careers as a result. Okay, that brings us to solutions and how to make solutions. And I've made mistakes. And I reason that frequently when I make mistakes, it's because I don't understand the system. I don't understand what a gram actually looks and feels like versus a milligram. Because I didn't, the math went wrong and I didn't catch it. I didn't catch that my answer is off by a decimal point, which is an order of magnitude. So, what is a solution? Well, to simplify, what we're really talking about is homogeneous mixtures of essentially fluids. And so the solutions that you'll be making in the laboratory, it's one phase, right? And so there'll be liquids. A liquid that is a homogeneous mixture, a solution. That means that there is a solute or solutes, more than one, dissolved in some kind of solvent. Okay? A solute or solutes dissolved in some kind of solvent. And usually, hey, the solvent is water. It means you can make solutions in organic solvents for the biotechnology workplace. The principles are all the same, but if you're dealing with things like micro or growing cells, preparing things for people in a bio laboratory, the solutions are almost invariably going to be aqueous, which actually makes things easier to understand because water has a bunch of unique properties that we'll talk about in a bit. So, what distinguishes one solution from another then is the identity of the solvent, let's say that it's water, the identity of the solute or solutes, because there can be more than one, and the quantities involved. Now, when we consider that, we arrive at a concept called concentration. And so frequently you'll be asked to make solutions of a particular concentration. What do we mean by concentration? Well, what we mean is quantity per unit volume. Now I noticed to my chagrin that I'm running over. Is everyone okay with that? Yes? Okay. Quantity per unit volume. And there are various ways of expressing it. One popular way of expressing this is called molarity. So if the quantity is in moles and the volume is in liters, that gives us molarity. And the symbol is M, big M. But there are other ways too. And so, for example, you may have to make solutions in grams per milliliter, or for simplicity, you may make solutions expressed as percent. What percent really means in this context is ratio weight to volume and another way that we make solutions disregards units entirely in favor of further simplicity, and instead the concentration is expressed as a multiple of the working concentration. So we have a stock and that stock is concentrated. It will be some factor more concentrated than the diluted working concentration. We call that X. X is another way of expressing relative concentration. So, in the interest of time, I'll get to the point. Realistically, what you'll be asked to do amounts to just a few different things. One thing you'll be asked to do is grab some crystal or powder. Here's one now. This is granular. Grab a dry powder and dissolve some amount of this to make a solution. So, from granules, crystals, pellets, etc. Dry, in other words. What you are really solving for is a weight. What weight in grams of this stuff do I need to weigh out physically and add to some volume of solvent to make a solution of a given molarity, of a target molarity? That weight in grams can be calculated in grams, which you need to use a scale, if and only if you consider the formula weight of the solute in grams per mole and multiply it by the target volume of the solution in liters and the molarity in moles per liter. Now this is actually handy if you look at it, because A, it relies on the metric system and you're now experts. B, this is a handy way of going to a chemistry class and taking a quiz or whatever, when someone says, what is the molarity of this solution? Well, molarity in moles per liter is equal to the weight in grams divided by the formula weight in grams per mole times the volume in liters. It's the same equation. And we use this to make stocks. Just as a chef doesn't make everything from scratch every single time, but keeps stocks of things that are concentrated, we do the same in the lab. And so we keep concentrated stocks of even sodium chloride in the lab, and we dilute from it. So let's consider making a stock solution of sodium chloride. The formula weight of sodium chloride, let's say for our purposes 58.44 grams. Now, a note here, back to real life. Containers like this will say FW equals and then not give you units. You know the units are going to be grams per mole, and another way of expressing that is Daltons. Anyway, you'll look and you'll see, okay, 58.44 grams. Make 250 milliliters of, what did I say? I did 3 molar. Make 250 milliliters of 3 molar sodium chloride. I'm going to use this equation, but I'm going to be literal about it. I'm going to use this equation. Notice I specified what your units absolutely must be. Your units must be as I wrote them. And as I gave you these values, well, they're not. But that's okay, because everything is metric. You can readily convert. And so ideally, you're not going to do little, equations and charts on your notebook. You'll just do it in your head. So the weight in grams of sodium chloride is going to be equal to the formula weight in grams per mole, so 58.44 grams per mole, times the volume in liters. I said 250 milliliters, but you know now that is 0.250 liters. And the molarity in moles per liter. Big M means moles per liter, so 3 moles. Now, the first few times, take a step back and eyeball that and say, does that make sense? Well, one way we can figure out whether it makes sense or not is see whether we end up with units that actually are desirable and make sense. Well, let's see what happens. We want to weight in grams. Here's our grams. Grams per mole. There's moles in a denominator here and a numerator there, so they'll cancel out. There's liters in a numerator here, a denominator there. They'll cancel out. The last unit standing is actually the unit we want, grams. So we've got a fighting chance of getting this right. It will be some answer in grams. And when you do this, if you're like me, you come up with 43.83.
Yeah.
That makes sense?
Yeah.
That's important. So, okay, if you are solving a problem on a quiz for a chemistry course, mind significant figures. Follow the rules that we went through. In real life, if you're making a complex solution with a bunch of solvents, use all your instruments to the limits of their resolution, because it doesn't take you any more time. Use all your instruments to the limits of their resolution, because it takes you the same amount of time. And then worry about significant digits. Make every operation and every measurement, in other words, as precise and accurate as possible. In other words, as close to the target and as reproducible as you can, every single time. Be mechanical about it, be methodical about it. Okay, so the formula weight of sodium hydroxide is actually not 40 grams per mole, but it's really, really close. It's 39. Anyway, let's make it 40 grams per mole. This stuff comes in pellets usually. You can buy it in pellets. Make 100 milliliters of 200 millimolar sodium hydroxide. So, the amount in grams of sodium hydroxide that we need to measure out is going to be 40 grams per mole times our target volume, which is 0.1 liters, times our target molarity, which is 200 millimolar, or 0.2 moles per liter. Do all that, you get 800 milligrams. You didn't, did you? You got 0.8 grams. My point is that that's exactly the same thing, and it should take zero thought to realize that. It should take zero thought to realize that. Okay. Now, once you've made a solution, well, now you've got it. So you're not going to make the same stock again unless you're out. Let's say you're not. Let's say you need to take a concentrated liquid stock and dilute it. Now, you're not dealing with measuring a dry crystal or a powder in grams. You're dealing with measuring volumes. And so you have a concentrated stock And you're going to take a little bit of that concentrated stock and make some target volume of a less concentrated working solution. You need a different way of measuring matter, and so you'll use like micropipetters or serological methods and so on, and a different way of calculating how much to use. But there is a way. From liquid stocks, C1V1 equals C2V2. C is concentration. V is volume. 1 is initial. 2 is final. It does not matter how you express concentration or volume to use this relationship, as long as you're consistent. It does not matter. So you can express volume in liters or microliters. It won't matter as long as both your volumes are either liters or microliters. You can express concentration as molarity and orders of magnitude thereof, or you can express your concentration in relative terms, we call that X, or percent. It does not matter. Likewise, the volume could be liters, milliliters, nanoliters, etc. It doesn't matter, as long as you're consistent across the equation. You know what the equation actually does is allow you to grab, let's say this is your stock concentrated solution. Answer this question. How much, what volume of this concentrated solution are you taking out to make a diluted solution? That's what V1 is. And frequently you're solving for V1. This is where the money's at. You're asking the question, how much of my concentrated stock am I taking out from my stock and using to make a diluted solution? So, make milliliters of 200 millimolar sodium hydroxide from a 2 molar stock. Notice we're not going from pellets anymore. We did that once, we've got the 2 molar stock. So this is what I came up with. for concentration, we're using molarity. So M1V1 equals M2V2. Fair enough. I'm solving for this amount here, V1. What volume of my concentrated stock do I need to make the diluted solution? All right. Well, okay. That means I'm solving for M2 times V2 over M1. M2 is my target molarity. That's 200 millimolar. V2 is my target volume. That's 150 milliliters. All right. I've got an issue here. Look. 2 molar, 200 millimolar. So my target molarity is expressed in millimolar. My initial stock's molarity is expressed in molar. I need to fix that mismatch. And so I can do that in my head because I understand the metric system. And so I'm going to choose to do something that's more cumbersome than I could have done. And I'll just go like this. I converted 2 molar, my initial concentration, to 2,000 millimolar because I could. I could have actually done it the other way, right? I could have converted 200 millimolar to 0.2 molar, which would have been more reasonable. But either way is fine, and either way will get you the same answer, won't it? It will get you $15 milliliters. Now, that's really quick. Do another problem and use other forms of expressing concentration. One that many students find a bit disconcerting because they haven't dealt with it in teaching labs is this concept of X. And so there are some solutions, for example, some buffers that are used for electrophoresis that may be stored as solutions that are 50 times as concentrated as they need to be to use them. So the stock is 50x. What that tells you is that frequently you'll be using the solution at 1x, right? And so you need to dilute that stock solution that is at 50x to 1x. Everyone agrees? Now you may not have gotten that exact answer as I expressed it, because what I could have done is this. Right? The target volume is 2 liters. Why did I convert to milliliters directly? Why did I do that step? And you don't have to. Because what this would give you is this answer here, which is mathematically true. The reason I did that is because I actually physically make things like this in an actual laboratory with actual instruments with my hands. And I know I can't measure 0.04 liters. What I can measure is 40 milliliters. And the second reason I converted directly to milliliters is because I wanted milliliters in my answer. because I realized something about dilutions. Your stock is always going to be more concentrated than what you're making. Your stock's going to be more concentrated. And here, look, it's a difference of an order of magnitude, isn't it? And so I guesstimated that I'm going to drop down to milliliters because I understood the metric system. And you get the same answer. Okay? Now, another unusual, at least initially, way of expressing concentration is percent. Let's deal with percent on its own because it can be a bit of a banana peel on which people can slip. All right, so really what we mean is percent weight to volume. Weight to volume. And that takes a bit of conceptualizing, doesn't it? Because weight is expressed in grams, and volume, we use liters, right? Well, let's say, okay, we use liters or divisions thereof, and so we'll use it in milliliters. We've still got an issue, don't we? How do you make that leap? The way to do it conceptually is to realize that we're talking essentially mostly about aqueous solutions. And even if we're not, there's a way to relate any solution to an aqueous solution having to do with what's called specific density. Anyway, because you understand the metric system, and you've considered the properties of water, you know the following. 1 gram of water is equivalent to 1 milliliter of water. But you already knew that because I told you. I told you today when I told you about going to the grocery store and buying 2 liters of soda, which is 2,000 milliliters, and I told you that weighs 2 kilograms, which is 2,000 grams. I told you the same thing in a different way. So you know that. And in fact, this is all under a specific set of conditions, pressure, temperature, and so on. In any case, that's equivalent to 1 cubic centimeter. For your intents and purposes, under normal everyday conditions, that's all true. Now, let's consider what a percent weight to volume solution actually is. Here's a beaker. There's your solvent. Your solvent's going to be water. That quantity is going to have a specific weight, an actual physical weight, okay? In fact, every milliliter is going to weigh a gram. Now, that is in theory pure water. But if you're going to dissolve something, if you're going to add a solute to pure water, you no longer have pure water. In fact, that's the point, right? You no longer have pure water. You've added something to it. To maintain the same volume, you're actually displacing an equivalent weight of water, aren't you? And that's the way to figure this out. That means that if this is 100 mils, that would be equivalent to 100 grams, isn't it? Right? 100 mils of water, 100 grams. Well, all right, what does percent literally mean? It's actually Latin. Percent means per 100. Percent means per 100. And so 1% is 1 per 100 of anything. And so we write it like that. Okay? Now, let's say you want to make 1% 1% weight per volume sodium chloride. 100 ml solution. All right. That 100 ml solution will have a weight of 100 grams. Sodium chloride is going to be a crystal. It's a powder. How much do you weigh so that what you've weighed is 1% of the solution? Well, the solution is 100 grams. 1% of 100 grams is 1 gram. So that gives you your rule of thumb. 1 gram in 100 mils is equivalent to 1% weight. Okay? Right. So, one solution that we make a lot in the laboratory is an aqueous solution of sodium didecyl sulfate, which is a detergent. That comes in a powder, and so make 2 liters of 20% SDS. And hang on, I've got, formula weight is 288 point, let's say 4 grams. SDS, make 2 liters of 20% SDS. So, there's a reason why I gave you the formula weight, and that's so you can trip over it, because it is absolutely useless to you for this calculation. You don't really care what the formula weight is. It does not matter. All you're considering is a specific ratio of weight of SDS per total volume of the solution. All right, well, the solution's total volume is 2 liters. It's an aqueous solution. How many grams does 2 liters of water weigh? 2,000 grams. Okay. How do you express 20% mathematically? It's 20 per 100. You see what just happened? And so you are going to measure out 400 grams of SDS.